This is my flight computer. It probably doesn't look like much, but it's capable of logging telemetry during a rocket's flight. The way I programmed it, it can log flight time, altitude, acceleration, and roll, and even more is possible. With my code, it uses all of these various sensors to detect when it's in various stages of flight, like liftoff, coast, and apogee. This flight computer is pretty basic. It doesn't account for errors in the sensor data. Usually flight computers use things called Kalman filters, allowing it to overall be more accurate. So what does it do? This will be loaded onto my next rocket. Through this SD card module, it will be able to log all of the data that it collects. It has a barometer and an IMU powered by an Arduino Nano. The Arduino Nano takes the data from the barometer and the IMU to detect when it's in various stages of flight, based on acceleration and barometric altitude. There's also a buzzer on board that allows me to know when the flight computer is ready for flight and when it detects that it has landed. Once it has landed, it will close the SD card file and it is ready for power off. Eventually, I can take that data, put it into my computer to verify that the flight computer and all of its measurements were correct. The barometer detects altitude using the pressure of the air. Based on the current air pressure, it will set a baseline and eventually be able to detect how many feet above ground level the rocket is. The IMU can detect relative positioning and acceleration based on its gyroscopes and accelerometers. So when I started building this flight computer, I had a few criteria for what the sensors would need. First of all, they would have to be easy to program with an Arduino using C++. They had to be cheap, easily accessible, and solderable to a perf board like this. The IMU needed a 16G limit. What this essentially means is that once the rocket hits 16 Gs or above, the IMU will stop logging past that, as that is its maximum limit. So I needed that limit to be high enough so that it would detect the acceleration of my rocket, and based on the open rocket simulation, the rocket would only be experiencing a max of 6 Gs. So I needed an IMU that would be able to log past that limit. My original plan was to use a 1S LiPo battery. I would use a module to convert the power coming from the header pins and the standard connector from the LiPo battery to GPIO that I could connect to the Arduino. Once the Arduino Nano and the RunCam receive 5 volts, the rest of the sensors that need 3.3 volts would be powered off of the Arduino Nano's 3.3 volt pin. But what is the RunCam? My plan for this rocket is to use a small RunCam Robin 3 implanted on the side of the tube to record footage looking down at the ground from the rocket. To do this, I need a DVR. Because the RunCam Robin 3 is usually used for FPV drones, I needed a DVR to be able to record the footage to an SD card. So the RunCam Robin 3 and the RunCam DVR both also need power, so that would also come from the 1S LiPo. However, once I created the wiring diagram, I had my doubts based on my limited electronics experience of if it would work consistently. Because the voltage is being boosted and then brought back down from the 1S LiPo to the Arduino and to the sensors, I had my doubts on whether that would brown out the system because it draws too much power, or if it would even work at all because of all those components in between. Also, once all the components arrived, the IMU, the barometer, and the SD card module, once I started wiring them on a breadboard, I realized that they all needed 5 volts anyway, so there was no reason to not use a bigger battery. After that, I decided to switch to a 9-volt battery using this board called Power MB-V2. At first, I thought it would be easy and convenient as I'd have multiple 5-volt connections coming from the sensors connecting to the Power MB-V2, and it made it easy to convert that battery power into 5 volts as it had onboard regulators. However, I didn't consider its proportions, size, and unnecessary weight, and realized later on that it was a mistake, so I swapped it out. I started wiring all the components using a breadboard before soldering to make sure that all the sensors worked together successfully and that I could code it so it would all work together. Previously, I didn't have much soldering experience, so this was the first time that I was soldering all the header pins onto the sensors. So I was just soldering the pins onto this MPU6050, the IMU, and there was a very small amount of solder between the VCC and the ground, so that shorted out the whole thing, which eventually came all the way back to the Arduino Nano. So when I plugged it in, there was a little bit of smoke and a pop, so now this is fried. Thankfully, this is pretty easy to replace, and I have multiple of these, but as I was soldering to the barometer, there was a small blob in between 2 of the pins that I didn't notice until much later. Once I wired the barometer to the Arduino Nano and powered it on, the blob that connected the 2 traces of the power and ground essentially short-circuited the whole system and fried the Arduino Nano. I hadn't noticed this blob until much later, but as soon as I powered it on, I heard a pop and a burnt electronic smell. I immediately unplugged it and inspected all the components until I saw the blob on the barometer. After that, I decided I learned my lesson and I wouldn't make that mistake again. Until the next day. So I was just working on this circuit. I was plugging in this buzzer over here, and I think what happened was, I unplugged it really quickly, but what happened was one of the wires came loose from here and then went to positive instead, and I think it was the main cable. So this ground that was powering this whole blue channel, the wire came loose and touched one of the contacts on the positive channel, which shorted out the whole 5-volt channel again. So I have another dead Arduino Nano. As I was wiring the entire circuit together with the sensors and Arduino onto the breadboard, but once I powered it on, I heard a pop and the all too familiar burnt electronic smell. The wire that was powering the whole ground terminal came loose. I powered it on, and then I moved the breadboard a little bit, causing the wire to touch one of the 5-volt contact pins. That short-circuited the Arduino as that was powering the 5-volt and ground rail, burning the second Arduino Nano. So yeah, I fried 2 Arduino Nanos and a BMP388 barometer in the process of building this, but I definitely learned my lesson. Once I'd finished creating the entire circuit, verifying that each sensor or component got power, I started programming. At first, I had a lot of problems with the microSD card that logged all the data. I was using this 128GB microSD card, formatted with a 32GB partition in FAT32. However, every time I ran the program, there was a very high chance that after the program was done, the microSD card would get corrupted and I would have to completely reformat it. At first I thought this was because sometimes the file didn't close properly, so I implemented some logic to flush the file every few lines, and I made sure to unplug the microSD card only after the file was closed. However, once the program was complete and the loop was running successfully, after the file closed, I was still getting these problems. So I switched from the 128GB microSD card to this 512MB microSD card. This immediately solved the problem. I stopped having the formatting issues, and the data would lock correctly without corruption every single time. So how did I wire all these sensors and the Arduino together? The various sensors use 2 protocols, I2C and SPI. The barometer and IMU both use I2C, which allows the signals to be shared onto one wire and all go to the Arduino Nano at once. This made it much easier to solder all the wires together, as I could wire the same pin essentially from the barometer to the IMU, and then all of that data together would be sent to the Arduino Nano. That protocol made it a lot easier to wire the sensors together with the Arduino. The SD card module uses SPI, a different protocol, that uses only a few wires to connect it to the Arduino Nano. Soldering was one of the longest processes when creating this flight computer, because I had to make sure there was space in between each wire and pin, to prevent a bridge and a repeat of the lesson I'd already learned. So my original plan for this was to make it just one long video about how I made the flight computer, but now that I'm editing it, I'm seeing that it would make more sense if I split it into 2 because the video is so long. So I'll be posting another video in a few days. It'll be covering how I programmed the flight computer. So stay tuned if you'd like to see that. Thank you so much for watching, and I'll see you soon.